Okay. Hi everyone. Today's speaker is Daniel. He will be talking about utilizing the lunar surface as an impact laboratory. So uh, you can start, Daniel. Thank
Okay.
you.
Yep. I'm Daniel Sheward. I'm a postdoctoral researcher at the University of Leicester in the UK. And I'm just going to give sort of an overview of what science we do using the lunar surface as an impact laboratory. So just a bit of an overview. Most people typically think of the solar system as having the planets in fairly clean orbits and all of the other debris and rocky material confined to either the asteroid belt, the Kuiper belt, or the Oort cloud. But in reality, the solar system is far more messy than this. There's a lot of material that is everywhere. We have asteroids that aren't constrained to just the asteroid belt. There's actually over 37,000 of them that have been found near Earth within zero point 0.3 AU that have been discovered. And these discoveries are limited by their size. The smallest of these objects that we can detect are only a few meters across. So anything smaller than that, we aren't able to detect. So the likelihood is that there's actually a lot more material out there. And much of this material has Earth crossing orbits, meaning that impacts can happen with these objects. So some of the smaller material that I was talking about is generally from things like comets and asteroids that have orbits that come close to us. As comets come near the sun, they get heated and outgas. That outgassing can throw out material, and that material essentially litters the orbit of the comet. Or with asteroids, you can have smaller impacts that don't fully break up, but these smaller fragments of ejecta can similarly litter the orbit. And these sizes can range from tiny little sub-millimeter particles all the way up to quite big boulders. And when the Earth passes through one of these orbits, we experience a meteor shower as some of this debris is thrown into the Earth's atmosphere. And there's over 950 known meteoroid streams, which are these orbits littered with debris, and then many that are candidates that we think might be there because there's a lot of material. And when these orbits get perturbated and material becomes much more sparse, they become unlinked to the orbit. They have orbits so far out that they can be whatever. And these are known as the sporadic background population. So even when the Earth and the Moon aren't moving through one of these orbits, there is always a low level of material that can and does hit the Earth and the Moon. So empty space isn't really that empty. It's full of little rocks that can impact. And each year we get 12 10 to the 6 kilograms of this material, about 12,000 tons. And most of this material is harmlessly ablated in the atmosphere as a meteor and doesn't even reach the ground. Whereas larger meteoroids, they can cause damage, not by impacting the surface, but by actually the heating causes the gases inside them to expand and they explode, and it's the shockwave that does a lot of damage. So we have things like the Tunguska event in 1908 that was caused by a 55-meter diameter asteroid, and Chelyabinsk more recently in 2013 that was just a 20-meter object. And then up to the biggest size range, there's dinosaur killing asteroids that impacted 65 million years ago, and that was only a 15-kilometer wide body. So these things can do a lot of damage, if not somewhat infrequent. So how do we observe meteors? They use all sky cameras And there's a few advantages and a few disadvantages of doing this. The trajectory of the meteor is very clear because you see the trail, you know the Earth's gravity, it's very easy to back propagate that orbit. And because of this trail, the actual apparent area that they take up in the sky is quite large, so it's easy enough to spot one. And observing them is really easy. You just point a camera at the sky. If there's no clouds, you can observe for meteors. And the light that they emit is from them ablating, so it actually tells us about the composition of these objects. But it is limited to what you can see, obviously. So you at the altitude that meteors are formed, you only get about 2.8 to 10 to the 6 kilometers squared of observing area. And because the meteoroids lose energy during transit in the atmosphere, it can become more difficult. You are losing mass, losing energy, so it's a lot less simple to reconstruct the initial energy and things like that. And because most of them fully ablate or ablate into a tiny little pebble that doesn't make a crater, there's no craters for people like me to be able to study. So the way that we get around this is by instead observing the moon for impacts. You get a much bigger observing area, which means that you just have a greater chance to actually witness an impact. And there's no atmosphere. So meteors don't ablate at all, and they hit the surface with their full kinetic energy. So there's craters there to be studied. So we can use it as essentially a gas gun, but at orbital velocities. And the gravitational effect from the moon is actually negligible for the orbit of these meteoroids. So we know very well where an impact is from observing it, and we know if there are orbits, these meteoroid streams active at the time, then we know that it can only hit certain points of the moon. And the light that's generated that we observe is proportional to the kinetic energy, and it's all released as a point source. So it's very easy to do photometry and things on them. There are downsides to this in that the observing conditions are a lot more constrained. You can't just point a camera at the sky, the moon has to be there. And if you want to actually get any of the meteorite left over from it, then you need probably $1 billion from NASA. It's not as easy as just getting a few people to walk through a field. And these events are a lot quicker than meteors, whereas a meteor is burning up for a second or two in the atmosphere. These impactors release all of their energy within 5 milliseconds. So it's a very quick event. And so to observe them, because they're so quick, we have to observe at fastish frame rates, typically about 25 to 30 frames per second. And the observations are very limited because they are quite faint flashes of light, typically between about fifth magnitude and 12th magnitude. We have to observe only on the night side of the moon and only when the phase of the moon is less than about 50 to 60%. So we're not getting too much stray light from the illuminated side of the moon. And we can only observe when the moon's above 10 degrees above the horizon. So if it's lower than that, the air mass just destroys most of the signal and it makes it much more difficult to detect. And typically, observations are done in R or I band. And I haven't got it on my slide here, but you can only observe during Earth night. And because these are such tiny, quick events, you actually need two cameras, two telescopes to confirm that what you have seen is actually an impact flash. Because it could very easily, if you've just got one camera, could be a cosmic ray, could be a satellite passing that the solar panels just happen to glint at that time, or it could be an aeroplane. So you need two cameras to be able to say it's definitely a flash. It's in the same place on the moon in both images, and it's not moving. And the way that the light is actually generated Because there's no atmosphere to slow the meteoroid, we get the full kinetic energy, and most of these meteoroids are traveling between 10 to 72 kilometers per second. So even a single gram of this material has the same energy released as half a kilogram of TNT. So these are very energetic things. And this energy is all released within a few milliseconds, and it excavates a crater, and some of the ejector is superheated to form a plasma. And this plasma gives off the light through incandescence. And if sufficiently energetic, we can see this light from Earth. And because it's caused by the incandescence, we can treat it as a black body. It's not perfectly a black body, but it's a good enough assumption that we can do a lot of science with it. So if we actually, because we already have two telescopes and two cameras to confirm the events, if we observe in different wavelengths on these cameras, we can then derive the temperature of the ejecta plume. And we found that most of the temperatures of these impact flashes are between 1725 Kelvin and 3776 Kelvin, which is nice because that is the melting point and vaporizing point of lunar regolith. So it makes sense that they should be between those temperatures. However, we have seen some that are outside this range. That is kind of an open question within lunar impact flashes, why we get this temperature anomaly sometimes. And it could be that it's a methodological error of either the two cameras are being treated as perfectly synchronized, so both frames of the flash are at the same point in its temperature evolution, but in fact that could be slightly misaligned, in which case you would get temperatures that aren't physically correct. It could be that the black body assumption is just not accurate for all cases, or it could be that there is just another physical process that we aren't taking into account. So when we see an impact flash, we can calculate the total luminous energy of that flash. By taking each frame of the LIF, we can get the apparent magnitude as we observe calibration stars during the observation period. And we can then take all of those magnitudes, plot them against time, fit a decay curve, and then try and reconstruct the missed light due to readout time of the camera. So these are very short events. So even if you have a pretty good readout period, you can still lose a lot of energy during that readout period. So once we have that reconstructed, so we have the actual energy curve, we can calculate the energy for each magnitude, for each event, sorry, and then sum them all over the entire duration to get the total energy. And this luminous energy is important because it's proportional to the kinetic energy, and its proportionality is given by this luminous efficiency function, eta, which this is currently one of the problems in the field, is that this eta term isn't very well constrained. There's about 2 orders of magnitude in uncertainty on different values that people use, which when converted to the kinetic energy, that is a big disparity in energy. So that's one of the problems that I've been trying to solve. Another thing that witnessing an impact flash tells us is we can sort of work backwards and try and determine which stream it came from. So because the gravity is negligible on meteoroids, it can only hit the hemisphere of the moon that is visible to the orbit of the meteoroids. So when an impact's observed, we can check which streams could be responsible. We look at which streams are active, so the ones that we're currently crossing the orbit of, which streams of those are visible to the impact location, and if there's multiple candidates, then we can check the zenith hourly rate, which is essentially just how much material hits on average from that stream. So you can have one stream that has a lot of material, a lot of impacts, another one that's very sparse material, very few impacts, and then we can say that it's probably the one with more material. But we can never say for certain, and we can never disregard the sporadic background. There is always a chance that even if there is a massive meteoroid stream with a lot of impactors, that it could still be an impact from something else. So once a stream has been identified as the most likely parent stream, we can take the impact velocity because we know the velocity of the group of meteoroids, and then we can adjust that for the moon's velocity. And we know the impactor density because these are all pieces of a parent body that have been ejected. So if we know that parent body, if we know the composition of that parent body, then we know the composition of all the impactors in its population. And we know the impact angle because we can calculate it just from where the stream is. And then with these, we can obtain the mass of the impactor with this kinetic energy equaling luminous energy over eta, and kinetic energy is a half mv squared. We know everything except mass, so it's just a simple case of solving for mass. And as we know the density as well, we can also get a average value for the size of the impactor. And by observing lots of lunar impact flashes, we also get an idea of the population of the Earth-Moon environment, which is important for safeguarding things like infrastructure and for future astronauts to the moon. It will be important to know where gets hit the most, where's relatively safer, and when the times are that there'll be more meteoroids potentially impacting. And you can see in the images on the right, that's the top image is one of the solar panels from the Hubble Space Telescope that had to be replaced because of micrometeorite impacts. The impactors that did this damage are sub-millimeter in scale. And similarly, in the bottom image, that is one of the window panels from a space shuttle that also had a micrometeorite impact. And these impact populations also tell us about the age of surfaces. So not so much at places like Earth and Venus that have a thick atmosphere to protect the surface and replenish, but on bodies like the Moon, like Mercury, that don't have these surface processes to replenish the surface, knowing where the impactors are, how often you expect to see impacts, allows us to calculate from what craters we see on the surface, how old the surface must be. And actually finding the craters themselves from a given impact is the bulk of what I do. It gives us a lot of information to be able to use the moon as an impact lab, because if we observe the lith, then we know when it occurred, the energy going in. And if we find the crater, we know the energy that came out, essentially. So it helps us refine the luminous efficiency and things like that. And it's great to use because Earth-based hypervelocity experiments, gas guns, can only reach about 8 kilometers per second. And even the slowest impacts on the moon are around 10 kilometers per second. So we're already quicker than we can currently achieve on Earth. But as I've said before, the luminous efficiency isn't well constrained, and the cratering relationship also isn't very well constrained. And to find the craters, it is actually quite difficult. If you want to find a crater on the moon, it's easy, but finding a specific crater is a lot more difficult. So we have to do something called temporal pair matching, which allows it to take two images like this that have a fresh crater in to something a bit more easy to read, where changes are a lot easier to find and you see a lot more of the actual structure in the image. So you can see the ray ejector from the crater rather than just the circular crater itself. And the way that we do this is with Lunar Reconnaissance Orbiter images. The Lunar Reconnaissance Orbiter has been in orbit since 2009. It's got a host of instruments, but the one that's important to me is LROC, the camera. It's made up of three parts, the wide angle camera, and it has two narrow angle cameras. The wide angle camera gives 100 meters per pixel, and you get about a 100 kilometer image width. And the narrow angle cameras, which are the more important ones, in my opinion, are 0.5 meter per pixel, and you get a 2.5 kilometer image width, and two of those next to each other, so effectively 5 kilometers. And the LRO has an orbital period of 2 hours approximately. So each month we get a fully mapped moon from the wide angle camera and about 50% of the surface mapped from the narrow angle camera, which the narrow angle camera doesn't actually reach above 85 degrees or below minus 85 degrees latitude. So we don't get a lot of information past those ranges, but within the main bulk of the moon, we get a lot of high resolution images. And these are released publicly on a 3-month delay every month. So in total, over 3 million images have been released from this satellite, which sounds like a lot of data, should make things easy, but in fact, I've gone out of order. In fact, it's not as easy as it sounds because you have these 3 million images in total. Once you consider that you need very narrow tolerances on which images can actually be used, like you need nadir pointing images and you need an incidence angle of greater than 50 degrees. That narrows the pool quite a bit. Once you actually consider that you need it of a specific location where the crater is estimated to be, that makes it a lot less, typically only about 15, 20 images that have both the before and after counterpart and has counterparts with a similar incidence angle. It means that there's very few actual images that can make temporal pairs. And so this image on the right is what we generally get when trying to make temporal images. The dotted line is a 2-degree square on the moon, and all of the marked locations are places where temporal pairs are possible, and everywhere else we're just unable to search. And so the importance of these constraints is that we can't actually make very good division images if we don't obey these. So the incidence angle is very important in making these because, as you can see on the image on the right, we have two images of the same location with different incidence angles. The one on the left is a high incidence angle. The one on the right is a low incidence angle. And it's quite difficult to actually tell that these are even the same place. So with the technique that we use where we want to fully align the images, so then we can divide pixel by pixel and get just a map of what has changed in the image. If you try doing it with two dissimilar incidence angles, everything has changed in the image, so you don't really gain anything. And so to simplify this process, as part of my PhD, I developed software called Pineapple to automate the process, the Python NAC automated pair lunar evaluator that basically takes just the latitude, longitude, and the epoch of an impact flash and will form every temporal pair that it can within a given tolerance around that location, and then processes it through ISIS-3 and basically outputs just the change map that you saw before that has all of the features that are the same will cancel out, and anything that's new will be highlighted within the image. And the problem with this is it's quite a slow process. It's quite computationally heavy because these are very big images, typically 5,000 by 25,000 pixels. So it takes around 2 hours per image pair. And for each location, you can get 100 image pairs. So for a single impact flash, it can take quite a long time to actually process all of this data. The other problem, benefit, depends how you look at it, is that there are over 850 impact flashes that have been reported within literature or online databases. And there's quite a few observation campaigns that exist. There's Neliota in Greece, Midas in Spain, the Meteoroid Environment Office for NASA, and in a couple of years' time, we'll also have Lumio, which is a CubeSat to go and observe impact flashes on the far side of the moon. So we'll have a lot more data from those. And this is also something that is quite simple for amateur astronomers to observe. So we get a lot of amateur astronomers helping us out with observations, taking their own observations. And it's something quite easy to do. So there's a big wealth of data for us to process through. But 850 lifts, 100-ish temporal pairs per image, 2 hours per temporal pair, that's a long time to be processing. So we had to select which of the impact flashes have the highest likelihood of being located. The faintest detectable lifts will only form craters about 1 meter to 2 meter in diameter. So it's very close to the resolution of the narrow angle camera. So when you get an image like these in the bottom right of the smallest craters, it will just be a black blob. You can't measure the actual size of the crater. In the occasions that you can, it can be wildly inaccurate because you're very close to the resolution. So we, to sort of filter the data set somewhat, we excluded non-confirmed events. Didn't want to waste time on something that might have been a cosmic ray. We obviously we need before and after images. So we exclude any impact flashes that we've seen before LRO was in orbit. And we exclude events that have been reported but haven't had the data released because we won't be able to do much with them after we find the crater. And we prioritize the most energetic impact flashes because more energy is a bigger crater. A bigger crater is just easier to find. So we selected the 22 easiest to find impact flashes and ran them through Pineapple and managed to find 12 of the craters from these impacts. Now, the reason it's only 12 is we only get estimated coordinates, which those estimates can be wildly off. If you're seeing an impact flash very close to the lunar limb, then you have the parallax effect that means that the error on it is hundreds of kilometers. So it can be difficult to narrow down an estimated impact flash location and makes it not always easy to actually find the crater. But with these 12 craters, we can still do quite a bit of science. So because of this poorly constrained luminous efficiency turn eta, we want to try and use these as the first set of ground truth data that we really have at the moon. So we have the kinetic energy from what we've observed, the impact flash, we can calculate it, and we can measure the crater and see how much kinetic energy would have been needed to form that crater. However, there's still some issues with that methodology. The crater scaling laws are not the best. There's multiple of them that are all trying to do the same thing. Some of them are derived from lower impact lab velocity impact tests. Some of them are derived by explosive tests that they did in the 40s in the desert. Some of them are derived from greater than 1 kilometer craters on the moon or on other bodies. So it's not all necessarily applicable to the size scales that we're using, and they all tend to use different combinations of properties, and none of them tend to give the same values for a given crater. So we first need to use the observed craters to actually test which of these scaling laws is better. So because of these difference in parameters, making direct comparison is difficult, because all these craters have different densities, different impact angles, different velocities. So really doing a one-to-one test is quite difficult. But fortunately, of the 12 craters that we found, 2 of them were from the same meteoroid stream, most likely. So we can assign them the same group velocity, same density. We know their impact angle because we know the parent stream and we know the mass. So it's a lot easier to do a sort of preliminary test to see which of these scaling laws match up best to the data. So we did so and found that 3 scaling laws match the data quite well. Shoemaker and Wolf, Holsapple, and Opic, which it was quite surprising to me, because the typically used scaling law in lunar impact flashes previous to this was Melosh, which is shown to be quite off the mark, tends to be overestimating the crater diameter, which could be one of the reasons why we didn't find as many as we thought, because the material was actually making craters smaller than we were expecting. So with these 3 scaling laws, we can then move on and do a more comprehensive study. So we did a Monte Carlo simulation using all 12 of the craters that we'd found and randomly selected from the possible parent streams or the sporadic background. And from that, we get the velocity of the stream, the mass, the density, the impact angle, and the luminous energy. And we randomly selected a value for eta, calculated the predicted diameter from those values using each scaling law, and compared that to the measured diameter of the crater. And from that, we could calculate the chi-squared of the difference. And we found the median value for eta when below the chi-squared threshold is about 6 times 10 to the negative 3. Now, that is slightly outside the accepted range for the luminous efficiency as what's been used in literature previously. So why are we higher than what's typically accepted? Well, we know that the scaling laws aren't perfect, that none of them fit the data perfectly. So perhaps there's a new scaling law that we can make and base it on the ground truth data that we've seen. Or maybe the accepted range is simply wrong. This is the first study that's been done with ground truth data, so it's possible. But it's also possible that we simply didn't have a big enough sample size. Or it could be that we made a faulty assumption in thinking that the luminous efficiency is a set value. It could very well be variable based on things like velocity or impact density, or dependent on something that we just haven't considered thus far. So the way to answer the question of why we're higher is to simply get more data, keep running Pineapple, keep finding new craters, and try and get more of these to do a comprehensive study that is separated by individual streams. It could be that there's a stream dependency, and for each of these, we need to analyze each parameter independently to see if there's maybe something more going on that we haven't considered. And then the last thing that I want to talk about is seismology. So in the next 5 years, there's 4 seismometers that have currently gone through selection to go to the moon. There's Changi 7, which launches this year. There's the Farside Seismic Suite, which is currently slated for 2028. There's LEMS, which will be deployed by astronauts on the first Artemis landing mission, and SPSS that will be deployed by astronauts on the second Artemis landing mission. And if you get an impact flash that is big enough, you can actually see the resultant seismic waves on these seismometers. And this allows us to do a lot of really cool science because the lunar interior is not well studied at all. We don't know a lot about the crust or thickness and what's below. So this is a way to actually probe that. We can see the impacts on the seismometers and we get the energy, the precise time, and the location from observing the lifts. We see the seismic signal on the seismometer, and that means that we know the energy in, we know the energy out, so the only unknown is the crust. So we can use those observations to constrain the thickness of the crust and the interior of the moon. And this is a technique that's been done with InSight on Mars. It's actually the exact same seismometer on FSS that was on InSight. So these are very tested techniques. However, at the moon, we're able to observe the impacts, whereas on Mars, it's just an impact happens and they have to make a lot of assumptions about that impact. So we actually have a lot more data, so we'll be able to do a lot more accurate science. And it's not as simple as it sounds. Only very energetic lifts can be seen by the seismometer, and the frequency of these impacts is less. The bigger of an impact that you need, the frequency is a lot less. And these impacts need to be quote unquote close to the seismometer because the wave energy of the generated seismic signal drops off with 1 over r squared. So with these two constraints, we only actually expect to see about 70 impacts per year that both the seismometer will see and the impact flash cameras will see. And lift observations are performed only on the night side of the moon and are only possible around 5% of the time once you consider all of the other constraints for lift observing. And the South Pole always has some illumination. So these difficulties can be addressed. For the first three, we just need to observe more, get as much time observing so that when those on average 70 impacts happen, we're actually observing it. But if we're only able to observe 5% of the time, how are we supposed to do that? Well, that was another part of my PhD, to actually develop new techniques to be able to observe these impacts, to be able to maximize the time that we can spend observing. So we know from earlier that lifts behave like black bodies. And from temperature measurements, we know that the average temperature is around 2,750 Kelvin, which means that the peak emission from these impact flashes is typically around J band. And Rayleigh scattering, so the reason why the sky is bright and the reason why we can't observe during the day is wavelength dependent. So if you move to a longer wavelength, that means we have a darker sky. And if we have a darker sky and brighter flashes, then we actually increase the observable time to around 20% of a given month, which is a lot better, but it's still not good enough. So we have a project from the ERC now, the Listen Flash project, to develop the Tilt Network Twin Impact Lunar Telescope, which is made up of at least 3 stations around the globe. Whether we get some more is money dependent. And basically each station will house dual 40 centimeter Newtonian telescopes, each with 1 J-band camera and 1 R and I band camera. So we can get flashes all of the time, but still be able to make those temperature measurements. So with these stations, we should have 100% observation time on the moon if we spread them around the globe correctly. And obviously that's not considering weather. The image on the right is a mock-up of the old observing stations idea, but this is in flux, so I think some of the locations may change slightly. The one location that we currently have is Tilt 1 in Cologne, France, which is currently operational. We got the first results from the 2025 Geminids in December. The paper from that is currently under review with Amenras. And then Tilt 2 and Tilt 3 are currently in progress. Their telescopes are currently being built. Tilt 2 should be operational by late this year, and that will be somewhere in Western USA. And Tilt 3 will be midway through next year, and that will be somewhere in Australia, with possible additional stations, depending mostly on how much money we spend on these ones. And we'll also have associated institutes observing in a supplementary manner in case one station is clouded or offline for some reason. So just to conclude, the lunar surface makes an excellent impact lab. Impact flashes can be utilized for characterizing the Earth-Moon meteoroid environment, and crater locations can be used to refine loosely defined parameters in impact physics. And the upcoming lunar seismometers at lunar observatories will provide a lot of insight into the lunar interior. So thanks for listening, and any questions?
Thank you, Daniel, for the nice talk. Is there any question? I think there is one question in the chat, if you can see.
Yeah. Potentially, yeah. Could the Rubin Observatory contribute? Yes, absolutely. We're always looking for anyone to aid in observations. So drop me an email and we can talk about that. Yeah.
Okay, thank you. And is there any question? I have, maybe I might have missed this, but how often do these lunar impact flash occur? I mean, can we observe them, like, for instance, every night, or there is like
Uh,
a period or something?
so in general, they are about 8 per hour for the whole moon. So once you take into consideration we only see half the moon and then typically can only observe about a third to a half of it,
Mm-hmm.
you're expected about 1 or 2 per hour.
Oh, okay. Because you say you need to be sure for the flash to use two camera, right? Two different
Yes.
telescopes at the same time.
Yeah.
Okay. Thank you. Is there any question more? I think there is no more. Thank you for the nice talk.
No worries.
See you. Bye, everyone.